In this example, we're going to look at how to locate and classify the critical points of a function of two variables. So here we've got f of x and y equal to x cubed plus y cubed minus 3xy. The process overall looks very similar to what we do for a function of one variable when we use the second derivative test. The main differences are that when we're identifying critical points, we have to look at where both partial derivatives are either 0 or undefined, and when we're classifying critical points, we'll have to consider all three second partial derivatives. So let's see how this works. So to begin, let's locate the critical points. So to this end, we'll need the first partial derivative with respect to x, which is just 3x squared minus 3y, and the first partial derivative with respect to y, which is just 3y squared minus 3x. Both of these partial derivatives are defined for all values of x and y, so we're only going to find critical points when these are set equal to 0. So let's do that. So if we set these both equal to 0, we'll get two equations, and there'll be factors of 3 across both these, which we can cancel out, and so they'll end up just looking like x squared is equal to y from f sub x equal to 0, and y squared is equal to x from f sub y equal to 0. Let's call these equation 1 and equation 2. I've got two equations and two unknowns, so I should be able to solve this. As usual, the first step in solving a system of equations is to eliminate one of the variables. So let's take equation 1 and square it, and we'll get x to the power 4 is equal to y squared. And then if we use equation 2, which says y squared is equal to x, we can replace that right-hand side, y squared, with an x. So we get x to the power 4 is equal to x. So now we just need to solve this equation for x. Let's rewrite this as x to the power 4 minus x equals 0. Factor out an x. I've got x times x cubed minus 1 is equal to 0. And then we can also factor out an x minus 1. Multiply this by x squared plus x plus 1. So we've got two solutions here. X equal to 0 would satisfy this equation, and x equal to 1. This quadratic here is irreducible. If you were to try and find the roots of this, you'd end up with, in your quadratic formula, you know, the discriminant term that has square root b squared minus 4ac. In there you'd have b squared, which is 1, minus 4 times 1 times 1. So you'd have minus square root of 3. So there's no real value solutions to that quadratic term there. In other words, we can just ignore that piece. Our only solutions are x equals 0 and x equals 1. So now that we have x values for critical points, we can work out the y values for those critical points by using equation 1, which says that y is just equal to x squared. So in this first case, y is equal to x squared gives me y equals 0. And y is equal to x squared here gives me y is equal to 1. So I've got critical points at 0, 0 and 1, 1. So that's the first half of the problem done. Now we need to classify these critical points. And to do this, we need to look at some combination of the second partial derivatives. So let's calculate those first. So just as a quick reminder, we had partial derivative with respect to x was 3x squared minus 3y, and partial derivative with respect to y was 3y squared minus 3x. And our goal at the moment is to classify the critical points. So first step in that is to compute the second partial derivatives. So we've got second partial with respect to x twice is just going to give me 6x. The mixed partial derivative is going to give me minus 3, and the second partial with respect to y is going to give me 6y. So then for applying the second derivative test, I need to compute this quantity d, right, which we can think of as a function of x and y. These partial derivatives are also in general functions of x and y, and it's equal to second partial derivative with respect to x twice times second partial derivative with respect to y twice minus the square of the mixed partial derivative. And plugging in what we've just found, we'll end up with 36xy minus 9. So now we've got what we need to be able to classify our two critical points. Remember, our test will use this quantity d, as well as our second partial derivative with respect to x. All right, so for the point 0, 0, we've got d at 0, 0 is equal to 36 times 0 minus 9 is just minus 9. And there's no need to look at the second partial derivative with respect to x. If you get that this d quantity is less than 0, you can immediately conclude that you've got a saddle point. So that one's done. For the critical point at 1, 1, we'll get 36 times 1 times 1, which gives us 36 minus 9 is 27. So this is greater than 0. So now I also have to check my second partial derivative with respect to x at 1 and 1. And that works out to be 6. So that's greater than 0. And we can use our intuition from doing the second derivative test of a function of one variable, where the second derivative just tells us about the concavity. And remember, what you have there is that if the second derivative is positive, this means that the slopes of your tangent lines are increasing. So if that's your curve, slopes of your tangent lines are increasing. That's what your second derivative being greater than 0 meant. And from that picture, we can then see that this corresponds to a minimum. And that's exactly what the second derivative test for a function of two variables tells us as well. That because d and the second partial derivative of f with respect to x twice are both greater than 0, the point 1, 1 corresponds to a local minimum. All right, so that's it for locating and classifying these critical points. Just to help you visualize what we found here, I want to take a quick look at the graph of this function. So if we plot this function in 3 dimensions, it looks something like this over a limited range for x and y. So here's the x-axis, and here's the y-axis, and then we've got z going up. We can see our first critical point when x is equal to 0 and y is equal to 0. If we follow this along roughly at x equals 0 and y is equal to 0, we end up roughly around here. And that's where the saddle point is. And then if we look when x is equal to 1 and y is equal to 1, so that puts us sort of back over here. And we land down here in this valley. And that's our local minimum. So this is a very complicated surface, and this would be a very difficult thing to try and sketch without a computer. But the calculation we just did to figure out where these critical points were, which could prove very useful in a lot of applications, was not actually that bad to do. All right, so that's all I wanted to talk about in this example. Thanks a lot.